Today we'll be talking about the second part of supervised learning. Okay, I initially told you that supervised learning can be explained via classification and regression. Okay, so we are actually gonna differentiate between them. So yes, classification is more of a yes/no question or a true/false question. Okay, and I would like to take you back to the spam filtering example. Okay, which I gave in our first tutorial. So yes, uh, the machine, right, it generates self questions. These are self-generated questions by the machine, and it asks like, does the user like this kind of email, yes or no? Is the content worth reading, yes or no? And so on. Right, now it is all about taking some input and mapping it to some discrete set of values, discrete set of values. Like so this was some practical example. What if you just go out of your house, and then you go out of your house and check out people? How will you classify them? Maybe in terms of their gender, maybe in terms of their ethnicity, maybe in terms of the color of the hair they have. So that is all about classification. And when coming on to regression, okay, I'll be telling you about that. It's more of continuity. Okay, so last time we talked of an example of the population and area graph, where we had the graph to be somewhat quadratic in shape. And yes, the graph was made because of the points which we had, okay, around the particular graph. So, and I told you that if you know the area, if you know the particular area of so you can obviously plot and find the population it can carry, right? So that was with the help of regression. So here what we do is we have, okay, so yes, we have input, and that input, sorry, we have input, okay, that input is mapped to some real numbered values. Okay, so yes, now we'll be continuing with the MAR-IO program, which I talked of last time, and we'll be checking out classification and regression there. Obviously there are many things to be checked out, but since we just know about classification and regression, so we'll be talking about that.
And look at how the whole process started. This is what MAR-IO looked like at the beginning of its training session, all the way back in generation number 0. The program is probably even dumber than you thought at this point. Often it just stands there and doesn't even press any buttons. If MAR-IO stands still for too long, it'll cut off a simulation and try the next neural network, so it's mostly just jumping from one simulation to the next. But occasionally, the neural network says to press the right button, and the player starts walking right. Behavior isn't complicated, but it's enough to make at least some progress in the level. Let's take a look at a sample neural network to understand just how that works. This is one of the randomly generated neural networks that appeared in the first generation of the simulation. There are some green lines and a red line, and one neuron in the middle. Here's how it works. A green line is a positive connection, and a red line is a negative connection. A green line reading from a black or white square will turn its output the same color. A red line reading from a black or white square will turn its output the opposite color. In this case, the green lines read from the platform that the player is standing on and make the neural network press the right button as long as the player is standing on it. However, when the red line reads a black square representing one of those caped Koopas, it presses the A button and makes the player jump. This puts the player in a position where the green lines are no longer reading a white square, so the right button turns off and MAR-IO just stands there. This is a really basic example that illustrates how a more complicated neural network might operate. The more lines and neurons you have, the more nuanced the decisions can be. So, how exactly do we get those more complicated neural networks?
Okay, so I would like to speak in between that. What about classification can you check here? So your MAR-IO jumps when there are black boxes, right? So yes or no, obviously it jumps, and sometimes it doesn't when it is not able to connect through the green signals, right? The green neural networks. And what about when it skips over other hurdles? It does the same thing. So yes, obviously there are two choices for Mario: to connect to the green network or to connect to the red neural networks. So this is all about classification. Talking with regression, Mario's health rate, right, when it is mapped to distance he travels, it is about regression. Also, the awards it collects are also, with distance he travels is also a part of regression. So yes, let's continue.
The answer is evolution. When Mario gets further right on the screen, its fitness goes up. In this case, fitness is a function of how far right it gets and how quickly it gets there. Only the neural networks that produce the highest fitness are selected to be bred, creating the next generation. It took 34 generations of genetic breeding and fitness evaluation before Mario was able to finish the level without dying and get a fitness score above 4,000. You can see there were several places it got stuck for a few generations, but it always evolved out of those ruts. Let's take a look at a few of those ruts. You can look at the top left corner of the screen to see what generation number each rut occurred on. This process of picking the fittest individuals from each generation, breeding them together, and adding random mutations very closely matches the actual process of biological evolution that took single-celled organisms and produced intelligent humans. That's the power of neuroevolution. And though we don't yet have enough computational resources to produce something on the level of a human brain this way, it's kind of neat to see what it can do on one of my favorite games. I didn't come up with this idea on my own. This algorithm is called NEAT, which stands for Neuroevolution of Augmenting Topologies. And it's based on a paper by Kenneth Stanley and Risto Mikulainen. It's a really great paper that describes how to use genetic algorithms to build up neural networks from bare bones without presupposing the best structure for the neurons and their connections. It also includes some really cool ideas for separating genomes into species, which a lot of genetic algorithms don't really try and do. I wrote Mario from scratch in Lua as a plugin for an emulator called BizHawk. As I close out the video, let's take a look at the fittest neural network in each generation. It's kind of cool how sometimes you can see them make modifications to each other and improve performance, but sometimes an entirely new species becomes prominent and dominates the others. If you'd like to do more reading about the concepts I talked about in this video...
Okay, so I hope you've got the concept of classification and regression. We'll be talking about it further in the next lecture video 2, and I hope you like it. And then yes, unsupervised learning is coming all the way along, and have fun. Please subscribe.